Okay, welcome to JCA Connect. In the previous class, we were discussing about the disinfection by chlorine, and the chlorine is used for many applications. And in previous classes, we have discussed some of the advantages of chlorine comparing with the other disinfectant. Um, So chlorine is, of course, it is used to control the taste, odor, and the color. Okay. Chlorination is also used for an uh, oxidation of the ammonia. This is very important. Oxidation of ammonia, iron, manganese, sulfide, as well as the pure chemical. So that is why it has its own application in not only disinfecting the pathogens, it is also having the um, some important uh, pollutants that can be removed as well as controlled in the treatment process. So chlorine is cheap, effective, available in large quantities, non-toxic in low concentration to higher forms of life, and well residual. I already explained what is residual disinfectant. Okay, so major disadvantage is that it will remove the taste, odor, color, as well as including the disinfection process, as well as and it creates the residual chlorine. So I have already explained what is the importance of residual chlorine. Okay, to stop the further contamination in the pipeline after treatment process, the residual chlorine is utilized. The basic disadvantages of acid generation is the HCl and the formation of some of the trihalomethanes. Okay, that I'll explain how exactly in what process they are going to generate. So normally this process, what we are talking about, the generation of HCl, if the pH of the water, if it is less than 4.5, there is a possibility of generation of this HCl and a buildup of the dissolved solids and formation of potentially carcinogenic, halogenated organic compounds. The principal chlorine compounds used at water and wastewater plants are chlorine, sodium hypochlorite, calcium hypochlorite, and calcium dioxide. Okay. So whatever the sodium hypochlorite and calcium hypochlorite, these are our powder forms. Cl2 and ClO2, they are in gaseous forms. So free available chlorine. When the chlorine in the form of chlorine gas, okay, when the chlorine in the form of chlorine gas is added to the water, two reactions are going to take place. One is hydrolysis and the ionization. What is this hydrolysis reaction? So hydrolysis is the reaction in which the chlorine gas combines with water to form hypochlorous acid. It will form, okay, hypochlorous acid. This you have to remember. One is hydrolysis and one more is ionization. So hydrolysis means there is a formation of the hypochlorous acid. Hypochlorous is this one. Okay, hypochlorous is this one. Then after that, once it is formed, whatever this HOCl, this is going to dissociate. Normally, this also we can call it as ionization reaction. We can call it as dissociation reaction. Dissociation reaction. Then HOCl is going to give H plus and OCl minus. So the total quantity of HOCl and OCl present in water is called as free available chlorine. Okay, this we can call it as free available chlorine. The relative distribution of these two species is very important because the killing efficiency of HOCl is about 40 to 80% times than OCl. Okay, the statement you have to remember. They are vary with the temperature and pH. Okay, whatever the things it is there, it varies with temperature and pH. So that is why the whatever the disinfection is processed, it is dependent on the temperature as well as the pH. See, that is why this whatever the first reaction, that is the hydrolysis reaction, is very important. Okay, and once these are like a series reactions, what is formed? So the associate formed is going to do this way. Okay. Um, if you see the percentage distribution of hypochlorous acid and hypochlorite ion water as a function of pH at 0 degree centigrade, 20 degree centigrade. So you can see here pH. Okay. See pH. Assume that if it is 10, so then so the percentage of HOCl is it's around 0. If the pH is 8, then the distribution is 8. Here it will be. Okay, if the pH is 6, you can see here. Okay, the HOCl is 100%. Then you can see this stage what we are speaking about. This pH 6 to 8 is what we can call the optimum period or optimum pH for the better distribution of hypochlorous acid. See here also you can in the table also you can see. See this stretch. Okay, from here only you can start, not a problem. See this stretch, you can start with the 4.8 or roughly it is 5 point. Here it will be 5 point. So if you draw here to this portion, you can see it is the percentage of HOCl is more here. So at pH 6, so the HOCl is 98.8, pH 7 is 75.2, and 7.5 it is 49.1. So at pH 8 it is 23, at pH 9 it is 2.9. Okay. When it will reaches here, you can see that it's almost 0. Okay. And OCl, the OCl means you can call it as ionization reaction. So in ionization reactions, how the OCl percentage is there? It is 3.2, it is 24.8, it is 50.9, it is 76.8, and it is 97.1. Okay. Like this, the distribution is going to happen for the HOCl. Why we are speaking about the HOCl means that whenever you add chlorine into water, so the formation of HOCl is very important. So if HOCl formation is rapid and if it is more, so then we can say it is definitely um, um, and most very important component in chlorine disinfection process. So breakpoint chlorination. So the term of breakpoint chlorination is a term applied to the process whereby enough chlorine is added to react with all oxidizable substances such that if additional chlorine is added, it will remain as a free chlorine. Okay. And this we will have with the concept with the diagram itself. The main reason for adding the enough chlorine is to obtain free chlorine residual is that effective disinfection can be then be used. See, this it will remain as a free chlorine. Remember this. Okay. What we are talking about the residual chlorine. Okay. See, you'll add. Assume that you are adding 100 milligram per liter of chlorine. Okay. At some point, what will happen is that initially, even in the water, assume that in the water you have mm, pathogens will be there. Pathogens will be there. Then many um, components will be there. Many components will be there, plus components like you have Mn, manganese, calcium, uh, Cl chloride or Cl gas, chloride, plus some of the organic matter. So all the things will be there in a small traces. See, once you add 100 milligram per liter of Cl2, first initially it is going to kill the pathogens. It is going to kill the pathogens. Then it is going to oxidize the compounds. In the first slide itself, I have explained that it is going to disinfect or it is going to oxidize some of the other components along with the um, the killing of the pathogens. So once all the process is over, okay, once all the oxidizable matters as well as organic matter or the Mn and Cl or the Cs, if it is removed, okay, assume that 100 milligram per liter, you are adding to oxidize or to complete the process of disinfection. So then you will add 2 milligram per liter of Cl. So assuming that you are adding total 102. Assuming that you are adding 102. So 100 milligram per liter is used for completing the whole process. Then, so wherever when it reaches to 100, that point we can call it as breakpoint chlorination. So then whatever the 2 milligram per liter, whichever it is there, it is left as the residual chlorine to stop the further contamination in the pipelines. So that graph is there. In that graph, I'll explain how exactly it will be there. So breakpoint chlorination chemistry, when chlorine is added, okay, readily oxidizable substances such as Fe2 plus, Mn2 plus, H2S plus, and organic matter reacts with the chlorine and reduce the cost of its chloride ion at point A in the figure. Okay, this one. See, initially what will happen is that when you add the chlorine, this is the graph, the chlorine dose versus the chlorine residue. Okay, see how this graph can be arrived. See, what you can do is that you prepare two columns. Okay, one is that the dose, and second one is residual chlorine. Okay, see what you can do is that you take series of some vessels, so which has to be tightly capped. Okay, you take series of vessels which are tightly closed. About which are of, we can say, we always consider the BOD bottle. The BOD bottles are always have the 300 ml capacity. So you can take around 10. So like this, you can take 10. 1, 2, 3, 4, and 10. You consider 10 vessels. So then what you can do, you go on adding the increasing dose of chlorine to water. Okay, fill the water to this up to the neck. Fill the water up to the neck. Okay. Then what you can do, you add the increasing dose in terms of milligram per liter. For all, for example, you start with 5 milligram, 10, 15, 20, 30, 40, like that, you increase it. Okay. So then, once you add the iron doses, so let us start with 5, 10, 15, 20, 30, 40, 50, like that. You continue. Then residual chlorine. So what you can do is that, so whatever the water you have added initially, you just assume that it consists of the pathogens, it consists of iron, it consists of the manganese, and it consists of the organic matter also. Organic matter is nothing but it is the dead plants. Okay, dead food waste. That is nothing but it is the organic matter. Organic, it is always the carbon content will be more. Any biodegradable matter, we can call it as the um, organic matter. So initially, what will happen is that once you add the dose 5, 10, 15, and whatever the water you are taking, sample it is from the same source. If you are taking the water from the tank, or if you are considering the water from the any of the borewells, let it be a source one only. Okay, then go on adding 5, 10 with the increasing dose of the uh, disinfectant. So then once you add it, what you have to do is that mix it well and keep it in a dark room. All keep it in dark room. Keep it in dark room. Okay. Once you keep it in a dark room, okay, keep it for about half an hour. See, whatever the pathogens or organic matter or Fe, so it is going to oxidize, even it is going to kill the pathogens. Why you keep it in dark room means because these are light sensitive. Even if the pathogens are there, it is inactive in light. Even if it is there in a dark, so the chlorine is very active and the microbes will be inactive. Okay. Then initially what will happen is that when you add it, the graph will go like this. Okay. See, for the lowest dose, it will go at the point A. So initially it is going to oxidize iron, Mn. Okay. Initially it is not going to kill at this present. Remember. Okay. It is not going to kill at this present. So then after that, from A to B, here you can say at this stage, you can destruction of chlorine residual by reducing compounds. The reducing compounds means the Fe and all those things. And here, what will happen is that uh, combined residuals. See, combined residuals. It is nothing but after meeting this the point A. Remember, this is the point A where the oxidation of the Mn, Fe, and the other parameters are going to take place. So once it reaches to at the point A, then what will happen is that once it is oxidized, the added chlorine continues to react with the ammonia. Okay, ammonia to form the chloramines. Normally, in the most of if you see, take a surface water, if you're disinfecting. Okay, small traces of ammonia, it will be there. Okay, ammonia, or you can call it as the nitrate or ammonia nitrogen, that nitrate nitrogen. It is ammonia nitrogen. It is also one form of ammonia nitrogen. And it is continue to react with the ammonia to form chloramines between A and B. Okay, at that point you can see it is the A and B. Okay. Then for there, whatever it will form, it will form monochloramines and dichloramines in between that point. So between the point B and point C, some chloramines will convert it into nitrogen trichloride. Okay. See, from B to C, here nitrogen dichloride. It is the conversion is going to happen. Okay. The remaining chloramines will be oxidized to nitrous oxide and nitrogen. The chlorine will be reduced to chloride ion here. This is very important. Here you can say the chlorine will be reduced to chloride ion, where at the point C. Point C, you can observe there is a what we can call reduce the chloride ion. So with the continued addition of the chlorine, the most of the chloramines will oxidize at breakpoint and will result directly increase in the free available chlorine. Okay. See, once you increase it, what will happen is that what will happen here up to here, you can say the chlorine residual is increasing. See, what is this chlorine residual? See, assume that you have added 100 milligram per liter. Okay. Initially, it is going to oxidize at 1 milligram per liter. Okay, zero chlorine residual. Then when you go on increasing the dose, listen here, from when you go on increasing the dose here, the even the residual chlorine is also go on increasing. At some point what will happen is that at some point here, even if you increase the dose, but the chlorine residual is chlorine residual is decreasing, it means that the reaction is started from here. Okay, the reaction is started from here, where the killing of all the pathogens is going to happen. And at some point, if it is going to reach at this point, okay, see, even if we increase the dose of 7 milligram per liter and whatever it is, okay, what will happen is that once all the demand is completed, demand means normally we can call this as a chlorine demand. Chlorine demand means 2 chlorine is required to kill the pathogens. Once it reaches to this point, okay, you can say again the chlorine residual is go on increasing. Means there will not be any utilization of the chlorine because the demand is already completed here. Okay, the demand is already completed. So then, whatever after this, once it reaches to this point, whichever, even if you add extra, that will be a residual chlorine. Okay, if you add 7 milligram per liter at this point, assume that it is 7 milligram per liter. So then, that itself is a residual chlorine because it is not utilized. But suppose if we what will happen? Suppose 5 milligram per liter at this point, if you added at this point, if you added, then what will happen is that this to this, we can say the chlorine residual like 1, 2, say this much is this much, whatever it is that 2 milligram per liter. Okay, 2 milligram per liter is utilized here. Then remaining will be 3 milligram per liter. Okay, at this point you will get 3 milligram per liter. Like that you have to calculate it. So then whatever after this, it will be a residual chlorine. See, I said one experiment that 5, 10, 15, 30, you have to increase it and you have to find out the residual chlorine after each of the experiment. After each of the experiment, you have to find out the residual chlorine. Then you plot the graph. Okay, the dose of chlorine versus the residual chlorine. You should get the graph like this. Okay, always you should get graph like this. So then, when if you are getting the graph like this, then it is the complete what you can call the disinfection process. Typically, it has to follow this kind of graph. Okay, at this point we can call it as breakpoint chlorination. See, breakpoint means after that all the things will be residual chlorine. After this, everything will be residual chlorine only. Okay. These are the possible reactions which are going to happen in the breakpoint chlorination process. Of course, in detail is not required, but still, this whatever the formed HOCl, previously we discussed that's the hydrolysis. This HOCl ion is very important. Once the HOCl ion is formed, okay, how exactly HOCl is formed? So when it is H2O plus what you can call Cl2, so it will form HOCl. Just go back and see how HOCl is formed. Then HOCl, when it is going to combine with the ammonia, this is nothing but ammonia nitrogen. So it will form NH2Cl, H2O and H plus. Then NH2Cl plus HOCl is equal to NHCl2 plus H2O. Then finally you can see again HOCl is there and Cl minus. Okay, we can say this is chloride. Where the chloride is formed at breakpoint C. At breakpoint C, the chloride ion is formed. Now we can differentiate what is the difference between chlorine gas and chloride. Okay, how it is going to form. Okay, chlorine gas is different and chloride ion is different. Then overall reaction, say you can say summary of the equation, that is NH4 is equal to HOCl and forming chloride ion. So occasionally serious odor problems have developing during the breakpoint chlorination operation because of the formation of nitrogen trichloride and related compounds. The presence of additional compounds such as organic nitrogen will react with the chlorine may greatly alter the shape of the breakpoint curve. Okay. For example, this will play a very important role. So I said that it should follow the typical curve. Okay. It should follow the typical curve. But what will happen is that it is not going to follow that typical curve and will react with chlorine and may greatly alter the shape of the breakpoint curve. The amount of chlorine that must be added to reach the desired level of residual is called chlorine demand. Okay. See, I already explained that the amount of chlorine that must be added to reach the desired level of residual is called chlorine demand. Just you assume that the chlorine demand is nothing but how much uh, amount of chlorine is required to oxidize oxidize to kill pathogens plus residual. Okay. So initially what will happen? It is going to oxidize the Mn and Mn, iron and all those things. And it is going parallel, it is going to kill the pathogens. And we need the residual also. This we can call it as total uh, chlorine demand. Okay. So then factors affecting the disinfection of chlorine we'll discuss in the next class.